combination of dampers. So we'll talk about that one. So in some dynamic systems, we can encounter multiple dampers are being used. So for that cases, all the dampers are replaced by one or equivalent damper. So when these dampers appears in a combination, we can use a procedure similar to those we use in finding the equivalent spring constant of multiple spring to find a single equivalent damper, so that we will have done from the previous to get the value of the spring. So for example, if we have a two translational dampers with a dampening constant of, so if we have the constant dampening constant, for example, we have the dampening constant of our C sub 1 and C sub 2, okay, so that appear in a combination. So the equivalent dampening constant can be found by using your C equivalent. Okay. So for parallel dampers, okay, so using that one. Now for the parallel dampers, the equivalent dampening constant, so that will be C sub 1 plus your C sub 2. Now for the series dampers, so we have that will be 1 over the equivalent wave damper, that will be the summation of fractions of your dampers, okay, for C sub 1 and C sub 2. Now, sample problem. A precision milling machine is supported in a 4 shock mount as shown in figure. So this is the milling machine. You have your overarm spindle, then you have your cutter here, then this is the table which is moving in this direction back and forth. Then you have here the location of this support for the table, so that you can also adjust the Y direction or the elevation of the table. Then you have the support base here, which is they are all mounted in the same base. Then we have here under are the shock mounts for all the corners of our milling machine. Now the elasticity and the damping of each shock absorber can be modeled as a spring in a viscous damper. So the same that will be done before, that will be a combination now. So we can model this one. So we'll be modeling it, since it is being supported by a shock mount, so it has also an elasticity. Now I'm going to draw here to model these combinations of springs and damper here. So we have here the spring acting here. Right here, draw here. So we have the spring here. So I'm gonna name this one as my point A at this area. So I'm gonna write here that this will be my point A, and this will be our K sub 1. Okay. Then the symbol for the dampening, so we have here the symbol, so it's like a piston symbol, then connecting it to the ground and to the object. So I'm gonna write here as put a hatch here. So this will be my C sub 1. Okay. Now for the other points, so we have A and B and C and D. So this will be our B on this side. So I'm gonna draw here again the spring, and then you have your corresponding ground. So this is now our K sub 2, Then we have your dampening symbol. So this is the C sub 2. Then on the other area, other point, so we have here your C, point C. So we're going to draw again here the spring. Then we have the corresponding ground here. And this will be our K sub 3. And we have the corresponding damper here. I'm going to draw here our damper here. So we have that one. Connecting that one. So this is now our C sub 3 also. And for that point D, touch this one. Then I draw the spring here for this part. So this one will be our K sub 4. And we have the symbol for your dampening constant here. So this will be C of 4. Then we have here at the center, we have the corresponding the gravity, and also corresponding here below are the weight of the object that is being supported by the damper or the shock mount for the corners. And we are assuming that the center of the gravity, that the center of mass is located at this point, and also with the corresponding weight of that one. As you can see that all the spring shall be subjected to the movement of your up and down of your displacement of X, and it is also subjected to equal velocity respectively on the center of the mass. Now letting the FSI, this one, so let it be the force acting on the spring, and FDI for the force acting on the dampers, where it can be expressed our force on the spring is equal to the K of the spring, that will be the value of I, then multiply by the displacement, we have your X, so where your I is equal to the value of different location of damper 1, 2, 3, and 4. Now for the value of the damper, FDI, that will be the dampening constant. We have your C, that will be multiplied by the X, also the displacement or the velocity. Let's say this is now the velocity, so multiply by the velocity. Then we have your I, that is the numbers point, that will be 2, 1, 2, 3, and 4. So we can rewrite the total force acting on the spring. So that will be your Fs is equal now to your Fs1 plus your Fs2 plus your Fs3 plus your Fs4. The same also the total damper of total force that is also acting on our dampers, that will be your Fd, that will be Fd1 plus your Fd2 plus your Fd3 plus your Fd4. Now where our weight is equal to the summation of your force acting on the spring plus the force acting in our damper. And we can rewrite it here in our equation, the force that's acting, no, for your spring. So for the spring, we are force on the SI, that will be the force on the spring, that will be on point 1. Then we have the corresponding here of your damper, Fd, that will be 1. So you can also represent it like this one to properly address the equation or the free body diagram, so that we have the guide. So the same also I've done here at point A, B, C, and D. So we have this showing that the force is acting on our spring and dampers, so where they are located. Now, going back to this equation, so denoting that on the total vertical force, which is your W, is the one who's acting on acting on the support. So uh, we can show that our um, force acting on our spring is equal now to the K equivalent, then times the displacement. Now for the damper, Fd, so that will be C equivalent, or the dampening constant equivalent, then that will be multiplied by the velocity. Now remembering from our previous lecture, so for the combination string, we have the K equivalent will be the summation. No? So since we have here for a spring that is in parallel arrangement, here they are all in parallel, so we are now the summation of the value of every K of the spring. So we have the K equivalent of the system, so that will be K equivalent of the spring, that will be K sub 1 plus your K sub 2 plus your K sub 3, then plus the K sub 4. Then for the dampening constant, so we have the C equivalent, so the same also I was stating later. So we have the value, we have C sub 1 plus the C sub 2 plus the C sub 3 and plus the C sub 4. So we have now the representation solution to the free body diagram. Okay. So that will be the sample for the combination of spring with the combinations of dampers.